Carolina's Waffle House is our comp, and they're good. I mean, they're really good, especially their home fries. You get them like, you know, the smothered and covered and slathered, so you just put everything on it, from cheese to gravy to bacon, and just they're really good. But anyway, whenever somebody walks in there, everybody says morning, right? And so like when you're, you know, had a little bit of a rough night, and you go in there, everybody's like, morning, morning. It's like you just want to hit somebody. It's like, all right, it's enough with that. So whenever we do morning, that's what it reminds me of, is walking into the Waffle House. All right, let's see. Last time we were together, you're right, it was wonderful. Thank you. Last time we were together, it came up about the waste baskets and chairs, and so I went upstairs and I talked to Tim G, so I put him on the case, and hopefully waste baskets and chairs will start to populate the rooms again. So again, is almost anything. If I can try to look into it, help you with it, just let me know. Hopefully this will get sort of resolved. I don't know where the waste cans went, but probably somebody selling them out of their trunk in A lot. It's sort of, you know, sad. Someone didn't get tenure and they're just trying to supplement their income, or some waste paper baskets. You hate to see it. You hate to see it. All right, so any other problems, concerns before we start? No, it's Friday, right? It's just gonna roll with the flow right now. I wish it was a little windier out. I don't know if it's the way our buildings face or the way they're constructed, but when you walk in that door that faces A-Lot, it is like a wind tunnel. I mean, it was so windy, my hair almost moved this morning. Almost.
It's going up to 54 miles per hour.
Is it going up to the 50s? Huh? It was, well, I was getting pelted by, it was picking up the salt, and it was like sticking the side of my face. All right, the last time we were together, we were starting to just lightly, and I mean lightly, review into molecular forces, because again, ultimately, we want to be able to look at a molecule, and no matter what it binds to, I get back to, I don't care if it's an active site, a protein, a receptor, DNA, it does not make a difference to me, because you want to be able to just give a reasonable hypothesis on how this interaction is going to occur, okay? Now, it's the P1 year is sort of tough, because everything you get this year is foundational for really the crux of our didactic curriculum in P2, P3. And although it doesn't seem it right now, all of this stuff you'll be drawing back upon it throughout the pharmacotherapeutics sequence. Just 8 courses chock full of fun. So things like this. So the way we have them set up, for example, for pharmacotherapeutic sequences, is you'll start a disease state. Dr. Nguyen will come in and do the pharmacology. Right, so telling you how these drugs, their mechanisms of action and so forth. And then Dr. Mudit, usually, not exclusively, will come in and do the medicinal chemistry. So he'll start relating physical or observed properties to that of the drugs themselves. And then you'll get into the therapeutics part. So you'll always go back, you'll always draw on this. So hopefully you'll appreciate that later on. But for now, you just got to get through it. So when we ended, we were looking at intermolecular forces. We talked about charge transfer, sort of a special case, because it's literally that, it's a charge transfer, right? It's set up specifically for a ring system, aromatic ring system that's electron rich, and one that's extremely deficient. And you can get partially some of the pi electrons that go from one to the other. It actually set up a little small transient interaction, a charge. The ones we were most interested in are the traditional ones that you've already had, and my intent is to review, is hydrogen bonding, dipole-dipole, van der Waals or London dispersion, whatever your preference is in name. We ended, I believe, just that hydrogen bonding, and that's where we stopped, if I'm not mistaken. Agreed? Okay. So again, for hydrogen bonding, you're looking for a hydrogen to be, for our purposes, on an oxygen or a nitrogen. If it's on fluorine, again, it's just HF, who cares? So you need a hydrogen on an oxygen or a nitrogen. And what that sets up in terms of, bond polarity is that you got the hydrogen, the least electronegative nonmetal, and then you've got oxygen, which is the second most electronegative nonmetal, with nitrogen not too far behind it. More importantly then, not only do you have that polarity of that bond, you've got these wonderful non-bonded electrons on the oxygen or the nitrogen. And so what you have is a donating and accepting, and I said I always hate that term because nothing's giving anything up, it's more of a sharing, right? So the hydrogen on one, electron deficient hydrogen on one, is attracted to the electron rich atom on the other, and vice versa. So you both donate and you both accept. And in essence, whenever you think of these, no matter what we're talking about, whether it's hydrogen bonding, dipole-dipole, or Lennon dispersion, they're bar magnets. That's all they are, okay? And it really just, if you will, depends upon the strength of the bar magnet. But what you're talking about is something that always has a side that's electron rich or a side that's electron deficient. A side that's always north, a side that's always south. And ultimately it's going to align itself to complement south to north, north to south. That's all it is. It's nothing fancier than that. So we wanted to relate that to functional groups. The last time. So for hydrogen bonding, we did alcohols, okay, which is good because I did it before class today. No, I'm joking. We did alcohols, amines, carboxylic acid, just because that carbonyl OH. So it could do other things. It could be both ionic, but again, that OH could hydrogen bond. And we did amides, and I believe that's where that was it, right? And then I stopped, and there was these applause, and you stood up, and I got teary-eyed, and I had to leave. That's how I remember the end of the lecture. I don't know about anybody else, but that's my world. All right, so dipole-dipole. First, a sip of coffee before it gets too cold. That's good stuff. All right, dipole-dipole. For functional groups, if I went right over here, can you see? I'm not going to humor myself and pretend that I could fit between here and the border, right? It would have been fun to try, but okay, so dipole-dipole. At the center for functional groups of dipole-dipoles is this functional group. Anybody don't remember generically what this is called? Oh, that was a quick carbonyl. You got the carbonyl. And so what you have again on the carbonyl is you've got this nice electron-rich oxygen, right? So it's delta negative, got nice non-bonded electrons on it. It's much more electronegative than carbon. I believe this is 3.6, carbon I think is 2.5. And so this is delta positive. And because of its shape, a carbonyl is trigonal-planar, right? So it's flat, it's flat. It, if you will, literally sets itself up to be like a bar magnet. And so carbonyl compounds, when they interact with each other, they complement their polarities. So if another carbonyl would come along, and they'll do, oh yo, how you doing? And it'll be opposites attract, right? Opposites attract. My wife is thin and pretty. Opposites attract. All right, so some basic carbonyl compounds. got a carbonyl that has at least one hydrogen directly attached to it. Remember what this group is called? Aldehyde. Beautiful. Aldehyde. Got a carbonyl. Then it's got two alkyl groups, or two carbons directly attached to both sides of it. Ketone. You'll know this one because you had this in biochemistry. What's this one here? Carbonyl, oxygen, and an R group on that oxygen, not hydrogen. Ester. Ester. That's right. It used to amuse me to no end that in a person who taught me Oregon College, his daughter's name was Esther. Coincidence? I don't know. Obviously underneath here could be a carboxylic acid also, right? It's got a carbonyl. Sometimes it's really just about, I'll put it for the sake of completeness, and then also we could have the amide again. For these ones, it's really going to be dictated more about its environment. So if you got a carboxylic acid, but there's a basic moiety close by, it's going to be acid-base, it's going to be ionic. Right? If you got something that'll hydrogen bond, it'll hydrogen bond. If you lack those two things, then the potential is dipole-dipole. Same thing would be true for the amide. So they've got some duality to them. All right, so again now, so these carbonyl-containing compounds, any other carbonyls that you can think of? Me either. When these carbonyl-containing compounds come together, they will rotate to complement electron-rich oxygen to deficient carbon and vice versa. Okay, it's a dipole-dipole. These are literally behaving like bar magnets, nothing different. So, pecking order now, hydrogen bonding was the strongest, or is the strongest, nothing happened to it. Then comes dipole-dipole, bless somebody. Oh, what the heck, bless all of you. It's Friday. Could have used it for your test. I'm a day late, right? Is that yesterday, PP? Yeah. Yeah, that explains Dr. Zucker weeping in the hallway afterwards. Oh, I haven't heard a word about the scores.
It's true.
It's true? Oh, I'm so sorry. I should have kept my mouth shut. I apologize.
Want me to read the email to you?
No. I'm sorry. I apologize. I didn't mean. I was not picking at a scab. I was not picking at a scab. I'm sorry. Got an email. Wow.
Yeah. So, make sure you come to class.
No. Always. I always think for any program, you have to be your own advocate. If you're struggling, go see the professor. I mean, I know we've got some really miserable people. I mean, Drobich is so difficult to talk to. Never says, please come see me. Alfonso, myself, I'm pretty miserable. Dr. Zucker, go see the professors. They will help you. Again, it gets back to there's certain things we could do well that other schools can't, and one of those things is being student-centered, is having an open door policy. Take advantage of that. Be your own advocate. Okay? So if you're not doing well, seek help. We will help you. Unless for my test, then there's no help. It's just the way it is. All right, so now the last one, but no, please, be proactive, get help. Is going to be London dispersion or van der Waals. And of the three, it's the weakest, but it doesn't mean it's insignificant, it just means it's the weakest of the three. Often it's a great driving force in that most things are happening in an aqueous environment. And dipole-dipole tends to be with nonpolar molecules. So, I'm sorry, London dispersion tends to be nonpolar molecules. So they're contorting and doing their best to minimize the interaction between them and their aqueous environment. So in aggregate, it can be a pretty powerful interaction. The question becomes, unlike, remember my marker, unlike hydrogen bond or dipole-dipole, I don't have a molecule that has a permanent dipole moment. All right, I do not have a molecule that is always, as a part of it that's always electron rich, still no racers, or electron deficient. Right? So the question becomes, let's look at, let's look at methane. I'll get choked up on, it's just methane. Okay. Here's my methane. Methane class methane. And I look at this, and carbon has, in terms of electronegativity, is at 2.5, hydrogen is at 2.1, slightly more electronegative than hydrogen, but not significant. This molecule has perfect symmetry. It has no dipole moment. Remember, having a dipole moment is a vector quantity. You have to have both magnitude and direction. Right? That's, if you will, makes give the polarity to, like, again, if we refer back to bar magnets. There's a magnitude and direction to the polarity. This is not. They all cancel each other out. Right? Everything's pulling equal and opposite in all directions. So the question becomes, how does a molecule that is nonpolar neutral become attracted to a like molecule? Right? How does this occur? Why does it occur? So if I just do a little simple electron cloud around it, right? This is scratch my artistic filter. That's a little electron cloud. And it comes into proximity to another methane molecule. Okay, they come in proximity. Now, as they approach each other, they actually repel at first. All right? They repel each other. Opposites attract, therefore like things repel each other. North to north or south to south. They repel each other. But then they get to a certain place in space, and instead of being repulsive, it also becomes attractive. The question became why? Why is that occurring? And what happens is this. When you have a molecule that's nonpolar, that tells me at no time can I point to a part of it and say, hey, this is always delta positive, this is always delta negative. What's happening is the electron cloud is continuously moving. So it's possible at any given moment in time, my electron cloud is dense over here. If it's dense over on this side, then I'm deficient over this side, right? But then in an instant, now the electrons are over here. And I'm deficient over here. And then they're over here. And then I'm deficient over here. And on it goes, right? And so it just keeps changing. It makes that noise, but you got to put your ear close to the page. But it does. So it's moving. So what happens, as another nonpolar molecule approaches it, they start to synchronize their electron clouds, their electron density. So if this one becomes deficient on this side, this one pushes its electron cloud this way. Becomes deficient over here. And then as it becomes rich up there, or deficient, or I'm sorry, as it becomes deficient here, it pushes its electrons away, it becomes rich over here, and on and on and on. So what we call London dispersion is an induced dipole. Right? They induce their dipole, then they synchronize them. So because it's based upon the electron cloud, the larger the electron cloud, the more significant it is. Right? I give you an example. We'll go back to the fond days of biochemistry last semester. I don't know if that was a response to the biochemistry days or what, but
Sorry.
no, it's quite all right. I have that effect on people.
Now you're putting words in my mouth.
No, not words, just yawns. It's all right. It's all good. All right. So as the electron cloud becomes bigger, the interaction becomes more significant. I'll draw back to biochemistry. You're doing fatty acids. You go, oh, there are some fatty acids that are solids at room temperature, others that are liquids. All right, solids tend to be not short chain. If you think about short chains, there's only a small overlap. there's usually saturated long chains because there's more overlap between their electron clouds. If you have a trans double bond in there, it doesn't affect it. It doesn't change the shape of it. You can still get that overlap. But the cis, what did the cis do? You remember? The cis put a kink in it, right? And so all of a sudden, instead of having that nice overlap, you got a chain with a kink. Now there's less overlap. And those are the ones that tend to be liquids at room temperature. So the more or the larger that electron cloud, the more significant the interaction. So although of the three it's the weakest, it can be significant. All right, where does that leave us? Nowhere really. All right, what I first want to do is I sort of want to tie up the charge transfer. I just sort of want to show you application, if you will, why it's a concern. And like I said, it's I don't say it's contrived, it's just not extremely common. And then really get into like some different molecules, ones that are usually used for compounding, and say, all right, give me a likely interaction between this vehicle, right, this organic molecule that's used for compounding, and usually when you're compounding something, you're usually going after ADME, right? You try to affect its absorption, its distribution, excretion, metabolism, right? That's what you're trying to affect. And whatever that therapeutic agent is. So the good thing about this is that it's just a reasonable interaction. There's no way to really know unless you were to actually do the research and get a crystal of it and actually see what that exact interaction is like. Let's go to the charge transfer. The most common way you're going to see charge transfer is its effect what certain drugs have on iodine. So, iodine, critical for, I'm pointing to it, I'm close, right there, yeah, right. Thyroid, right? Okay, so, we've got iodine. There are certain drugs that contain a nitrogen, carbon, sulfur moiety, nitrogen, carbon, sulfur, nitrogen, carbon, sulfur, nitrogen, carbon, sulfur. That moiety can do a charge transfer for iodine. And so these drugs like disulfiram, tolfenate, they will have an unexpected toxicity to the thyroid because what they're doing is through charge transfer is they're binding free iodine. Okay? So this is the if you will, the instance of where you're most likely to see it, as opposed to I show you those two aromatic rings that were set up for charge transfer. It's something like this. Just keep this in the back of your mind because this will occur with the nitrogen, carbon, sulfur moiety is a common one in therapeutic agents. Okay. Usually, what happens is you do a replacement. Don't get choked up about it. Just it's okay. Good. Okay. Sulfur, I'm sorry. Yeah, there and there. So usually what happens in drugs is, and this is something we'll talk about next week, is we do something called bioisosterism. We conservatively replace atoms with other atoms to impart desirable physical properties. Usually if you got a carbonyl, carbon double bond oxygen, one of the common things to do is replace that oxygen with a sulfur. Very similar to the oxygen in terms of its electronegativity. It's got non-bonded pairs of electrons, but it's larger and more lipophilic. So if you want to increase the uptake of your drug, you usually go to a sulfur. You replace that oxygen. Also, if it is carbonyls are readily hydrolyzed. So you probably talked about peptidases in biochemistry, right? Chopping up those amide bonds, that's attacking that carbonyl. When you go to the sulfur, instead of the oxygen, it's much harder to cleave or attack that and cleave that bond. So it also then not only gives you increased lipophilicity and uptake in the cells, it will extend drug life. So this type of moiety, common. But then, in PT, they'll say, oh, by the way, this will affect the thyroid, and then they'll just be on their way. Well, why? This is the why. And a hand comes up back and says, hi. You're just saying hi? Yeah, hi. How you doing? I'm not now. We save those for the end of the class. I'm joking, please. Yeah, well, I'll go back to, let me go back. Come back. Oh, here it is. It goes back to what I said about this on Wednesday. Yes, I had to think about what today was for a second. I did. It was so awesome. Last Friday, when we came back after the 2 days of snow, yes, nothing better in this world than a snow day, is someone said hello to me and said, hey, how's your day going? I said, not bad for a Monday. And then I realized it wasn't Monday, it was Friday. That was like the best feeling, because you had 2 days off, so I was like, dude, today's Monday. So, back to this, sorry. I'll finally answer your question. Just no. So, these are all chelators, right? So the question becomes, do I want you to memorize these chelators, or do I want you to memorize these compounds? And the answer is no. What I want to do is I want to go to the next step. I want to give you a compound and say, based upon what you're seeing, hypothesize a use for it. What's a possible use? And as we said with these ones, okay, with these ones, oh, let me turn this on for a second. There we go. With these chelators, we have these nice oxygen, nitrogen, right? Sulfur, nitrogen, oxygen, all these wonderful groups with these non-bonded electrons. Sulfur, OH, sulfur, OH. So they have the potential of being chelators, of binding metals. Okay? I could give you some other drug other than this and say, what is a possible toxicity? And instead of memorizing these exact drugs, you just go, oh, look at that. That has a moiety that has a nitrogen, carbon, sulfur. That could potentially do a charge transfer with iodine. Does that sort of make sense? It's the application. I'm not going to tell you the wall is red and then ask you on the test what color is the wall. Can I? That'd be like a bonus question. Extra credit? But it's more like that. It's the application, okay? Because it makes you, I don't know. It's more of an advanced. You're more of an advanced learner as opposed to being a rote learner. So that's what I would be looking for. That goes back to, as we go through this. Please ask me, I guess because I put a lot of background material in here too. Is this something like, that we need to know that you'll ask me, or how would you want us to apply this, or how might we see this on a test? I have no problem with that whatsoever. Okay, I have no problem sharing with you what I think is important and what I'll likely ask a question on. All right, my purpose is not to see what you don't know, so I want to see what you do know. Okay. All right. So let's do a couple examples. One is usually a compounding vehicle, the other is the therapeutic agent. I want you just to hypothesize, just between friends here. What would be the likely interaction between the two? So I got butazine, picric. Now, this right over here, butazine, this is picric acid. Picric acid is nasty. In fact, it's highly explosive. I remember when I started grad school, we had to watch these safety films. And they show when picric acid is wet, it's not a problem. When it gets dry, it's highly explosive. And they showed a safety film. They had this tiny little vial of picric acid. They put it in this old Cadillac and they detonated it and it just blew it up. It's like, whoa. So, why do I tell you this? My first summer grad school, I get perhaps the worst TA position ever. It was in Carolina. We had something called the long room. The long room was that. It was just a really long room. And that's where old chemicals went to die. So as people, moved out old chemicals from their lab, they threw into the long room. As people left and went elsewhere, we took their chemicals and put them in the long room. And it had been collecting chemicals for like 50 years. And so myself and my buddy, they give the great assignment of, we have to go in, catalog what's in the long room, and clean it up, right? And so they tell us though, you know what? Put fans on so there's ventilation, but don't spend more than 30 minutes in there during the day. Like, well, what's magical, right? After 30, something bad happens, why not at 25? What's this magical time of 30 minutes? So we start doing it. We come across this huge bottle, and it's got all these yellow crystals around the cap and everything, and it is picric acid. The slightest little turn would have taken us out, would have taken the whole floor out, right? So we're like, oh my God. So we're panicked, so we call public safety. What do? We gotta dispose of this. And the guy goes, just put it in a bucket of water and turn the cap. In which I responded out of reflex, out of your effing mind? So, nasty stuff. Nasty stuff. They actually came there then and did that, but I wasn't gonna do it. For what they were paying me to be a TA, are you kidding me? Anyway, so, I've got picric acid. This is just it's an anesthetic, antiseptic, anesthetic, right? It's commonly used low dose for burns. If you look at these two molecules, here you go, now time to earn your keep. Give me a reasonable interaction between these two. See, that would be the type of question which gets back to your original question. I give you two molecules, not something you've seen before, and I say, give me a reasonable interaction. I'm not asking you for the exact ones. There will be some that I do want you to know, and I'll let you know that though. What do we think? People talk to me. Come on, we never talk anymore. There's nothing bad happens with a wrong answer. I promise you.
You put them together.
So as they come together, what do you think is the interaction between the two? What are the intermolecular forces? Just yell it out. Nothing, I swear nothing bad happens. I swear, but that's beside the point. Nothing bad happens either. Pardon me?
Hydrogen bonding.
Hydrogen bonding. So what you're focusing on, I'll put words in your mouth. I believe it's this OH to this NH2.
Yeah.
Very reasonable. I like that answer. That is a reasonable answer.
What about the carbonyl, the OH?
Carbonyl. So this carbonyl, now we didn't talk about tweeners, but you could have tweeners, right? So carbonyls can accept a hydrogen bond. So if I got my carbonyl, the carbonyl can accept the hydrogen bond. It's one-sided, but it can. So that's a possibility. Of those two, what would be more prevalent if they were to come together? Do you think straight up hydrogen bond or the hydrogen bond to the carbonyl? Right. Now, only because this is picric acid. Possibility also exists is charge transfer. All right, remember I got these 3 nitro groups there? They're extremely electron withdrawing. All right, so this ring system is deficient. If you remember, oh geez, I love bring back electrophilic reactions. But these groups can be electron donating, making this ring a little bit more richer. So charge transfer is a possibility. But that would be the perfect question. What's a reasonable interaction? Hydrogen bonding, that's reasonable. Charge transfer, that's reasonable. You see what I'm getting at? This is fun. You want to do more?
Yes.
Thank you.
Yes, I
I appreciate the enthusiasm. All right, so I've got caffeine. That's a good idea, actually. This is gentisic acid, this is caffeine. This is before your days. So now if you just want to, you need a little boost of caffeine, you just do like one of those 5-hour ones, right? In my day, you used to have to chew these terribly bitter tablets. They were like gum, but it was just bitter. But anyway, so let's look at these two. One, I think, well, several I think you'll be able to get. The one that's most likely is you won't, but that's okay. I look at these two, and I say, okay, how will caffeine interact with gentisic acid? And again, you notice there's always the reason, right? It makes this then, it's supposed to mask the bitter taste of the caffeine. It did not. Give me some possibilities.
Electron pair of nitrogen by itself.
This is a basic nitrogen. What do you want? You want to do what with this?
Never mind.
No, you're going to dabble in the one it really is.
Yeah, the electron pair, there's an electron pair on there, right?
Yes.
Should be. That's gonna go somewhere. over
That is true. But no, so I'll give you the actual. I'll give you the actual, and then we'll do a couple hypotheticals. All right. So it turns out this is a basic nitrogen, and I have an acidic carboxylic acid. So I'm actually going to get an ionic interaction. All right. So I'm just going to get an acid base. I'm going to have something positively charged, something negatively charged. However, back to then, I wouldn't expect you to know that. I wouldn't expect you to know that this is a basic nitrogen, and that could occur. But back to what you were saying. So you're saying there's a non-bonded pair of electrons here. It might be able to accept the hydrogen bond from either here or here. Or, similar to that, the carbonyl oxygens could accept a hydrogen from here, from here or here, or possibly here. True? Perfect. Are we following what I'm thinking? Okay. All right, let's do a little benzocaine and salicylate, sodium salicylate. And again, if you notice all of these, they're always something to do with ADME, whether it's some affected absorption, distribution, metabolism, excretion. There's always a reason for this type of compounding. That'll be the joy of P2 fall. Give me a possible interaction. Nobody? Bueller. How about this OH and this amino group? What are we feeling here? Hydrogen bond to each other? I think so. To a lesser extent. Possibility, because that's what we're talking about, possibilities. I got two carbonyls, right? So I could, it depends how it orientates itself, I could envision in my head that it's possible that I could facilitate, be a little hard, but possible, hydrogen bonding and then some type of dipole-dipole interaction. But the hydrogen bonding being the most prevalent one, right? You're saying, this is fun, let's do more. Okay, all right. Don't get upset. We'll meet again on Monday. It's okay. I'll give you another lecture. I'm not done yet. It's okay. I appreciate it, though. Now I'm getting choked up. I wish you wouldn't have done that. I'm going to get all weak now. I didn't know I was having that profound of an effect. It makes it all worthwhile. All right. These I want you to know. Okay? So whatever you got, you could underscore, exclamation points. Stars are fun. All right. Not the examples, but I'm going to talk about some polymers. I want you to know the polymers. So polyethylene glycols, povidone, and there's another one on the other page I'm going to want you to know. I want you to be able to recognize those polymers. Why? Well, P2 compounding lab, you're going to be using them like crazy. They're very, very common. Okay? All right. So this is polyethylene glycol. N could be like 50 to 500, right? So these chains could be significantly long, okay? PEG's a very common one to use. When you have something that is highly, or you're having difficulty solubilizing, and you can revert to PEG to try to get that to go in a solution for you. Have you had Dr. Dunn yet for any lectures?
No.
Dr. Dunn, perhaps better known as Uncle Joe, the nicest man in the world, right? And so Dr. Dunn and myself, we've collaborated, done research together since the mid-90s, right? So we make this really great drug. Its name doesn't mean anything. It's called M47 because that's its notebook reference. That's M47. This thing shows great activity across all different cell lines, but stubborn ones like metastatic breast, pancreatic, and so forth, lung, metastatic lung actually. Fantastic profile. But what I made was pretty much dirt. It's dirt. I can't get it to go in anything. We never could, right? Polyethylene glycol, povidone, all the other ones that we're going to mention. Just fantastic drug, but we can't solubilize it. So at no time can I predict exactly what concentration I'm delivering, and hence it'll never make it to the clinic. But a fantastic profile. So as part of it is always critical as you're doing drug development. You could have the most fantastic drug, but if you can't get it into a solution, or you can't get it to where it needs to go, or have a long enough half-life, or what have you, if it doesn't have the proper pharmacological activities, don't make a difference. It just sits on the shelf, it's worthless. Like M47. It's a great drug, but it's dirt. All right, so PEG. I don't like this. I don't like this representation, because ultimately I'm going to ask you, how does this polymer interact with the particular drug? In this case, phenobarbital. What people focus on, like, oh, they think OH, hydrogen bond. No, this is an extremely long chain of oxygen, CH2 oxygen, CH2, CH2 oxygen, CH2, CH2 oxygen, CH2, CH2 oxygen. So this is sort of a very bad way to abbreviate this, because again, N could be from 50 to 500. So if you just focus on this part, because this is really what it looks like, what it has here is all these wonderful electron-rich oxygens, right? So they could either accept hydrogen bonds, but they themselves, you have wonderful dipole moments because these oxygens are rich, these carbons are deficient, so they can do dipole-dipole, all right? So, a terrible representation, my apologies. Better representation. So, I want you to be able to recognize this polymer. I say, hey, what's this polymer? And you say, hey, it's polyethylene glycol. Hey, thank you. All right, give me a reasonable interaction between phenobarbital and PEG. This was common usually, like if you had like a spasmodic bowel, irritable bowel. Sometimes you'd be given this mixture to calm things down initially. Talk to me.
To the lone pairs on the oxygens of the polyethylene glycol, do they go to, I don't know, the nitrogens over there and grab a hydrogen? No, probably not. Do they attack the base of the carbonyl and push that bond up, so the carbonyls need to grab hydrogens? I mean,
I like both things you said. So, what you're thinking is, one possibility is these oxygens could accept a hydrogen from either here or here, right, from these anions.
right.
Like it, very good. Or then you were thinking dipole-dipole interaction. The dipoles of this could match up with the dipoles of these carbonyls. Perfect, that's a perfect answer. So you did know. You thought you didn't know, but you did know. All right, next one is povidone. Povidone is just a repeating pyrrolidine ring system. It's just a repeating pyrrolidine ring system. It's just a repeating, and it's a repeating. Okay. As you look at povidone, one, it gives you a little bit of lipophilicity. when you use it, right? So you got a part of it that's it's rather lipophilic in nature. So to help you get into cross-cell membranes. You always walk that fine line though, right? So if you compound something, if it's too polar, it can't cross the membrane. Not polar enough, or not non-polar enough, and it can't get through, right? Unless you got some taking advantage of vacuum transport, would have you. And then you get into, will go in a serum, not go in a serum, and on and on and on. So you always walk this fine line. Dr. Moody will give you a rule, it's called Lipinski's rule, of what functional groups, how many functional groups you have to have in a molecule in order for you to be able to formulate it. But I don't want to steal this thunder. Povidone, here's betadine. Betadine is a polymer of iodine with povidone. And this one's actually sort of neat in that it's sort of an ionic interaction. The iodine here, iodine can go up to a trimer, take on a negative charge, and then the povidone is protonated, and I get an ionic interaction between the iodine and the povidone. But it's just betadine. So you'll see a little bit of betadine in your days. That one I wouldn't expect you. But let's say, making this up, it was phenobarbital and povidone, talk to me. Can't see the top.
15.
We'll try to finish up one more quick one. What's after me?
Calculations.
Calculations.
2 + 2 is 4.
Dr. Leopold. Can't get no nicer man on this world than Dr. Leopold. I know I said that about Dr. Dunn. I also say that about Dr. Leopold. You might think I like the people I work with. Hence, there's a reason why I work with them. All right. In this case, you might expect carbonyl-carbonyl, right? Dipole-dipole type interaction. Reasonable. All right. Let's just do one last one, and then we'll call it a weekend. Carboxymethylcellulose. All right, carboxymethylcellulose is a repeating polymer of glucose-like rings. I say glucose-like because if you look at the R here, if you look at the R's, these could either be H, so this is OH, 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 so it just looks like a long polymer of glucose, right? Or though it could also be periodically a carboxylic acid. So it's it could be a very strong hydrogen bond former. Also though, it could be partly ionic, okay? But when you think carboxymethylcellulose, really think hydrogen bond. That's the big one there. So, neurosilin here, this is actually, penicillin for vets. Vets use this for animals, large animals. But anyway, it's formulated using carboxymethylcellulose. But anyway, look at procaine and carboxymethylcellulose. Talk to me about possible interactions. It's okay if you want to say it, don't mind.
I'm gonna give other people a chance.
They're waiting for you to say it. Yeah, they all went, yeah.
Okay. So you can, if we take the, double bond the electron pairs from the oxygens there. No, other oxygen. Other oxygen.
On this molecule, this molecule?
That molecule.
This molecule?
Yep.
Yep, yep, yep.
You can grab hydrogens if we're focusing on the hydrogen aspect of it. You can pull from that nitrogen over on the end, other nitrogen, that nitrogen. I mean, there's a lot of options.
And then also, this is an OH.
Yeah,
This could hydrogen bond to.
that one.
There you
Yep.
go. Okay. All right. Tetracycline is also used as a compounding agent. Tetracycline itself is an antibiotic. It has pharmacological effects, so it's not very common. So I'm going to skip this one, okay? I don't really care about it. So those three. So again now, is in terms of would you expect me to recognize? I would expect you to recognize polyethylene glycol I would expect you to recognize povidone, and I would expect you to recognize carboxymethylcellulose. I'll tell you the exam question right now, and give you carboxymethylcellulose or one of those other two, give you a drug, and say, what is a reasonable interaction between these two? And then, just to make sure that you just don't go like, oh, hydrogen bond, I'll say, well, hydrogen bond between this atom and that atom, or dipole-dipole between this and this. So, but that's it. So that's ultimately what that question will look like, okay? You had enough fun? Yes, I'm sorry, I got a question, please.
Because we went through so many different options, will there only be one right answer on the exam?
I'll say like give the most prominent, the most reasonable. So in other words, we know the pecking order now. We know that, I gotta bend my knee, sorry. Oh, I just gave all the answers to the test, don't share them. We know the pecking order is hydrogen bonding stronger than dipole-dipole, which is stronger than van der Waals, right? So if I said give the most prominent, or ionic would be above those three also, or the most reasonable, something of that nature, then I'm looking for the most pronounced one, okay? So in that case there, when we had multiples, we had one where a carbonyl oxygen could accept the hydrogen, so I either get partial acceptor donor, and then I got two other moieties that can actually do an acceptor donor true hydrogen bond. That would have been the answer, that would have been the most prominent one, okay? That's what I'd be looking for, yes?
So if we had to put the OR group onto the ester group, wouldn't that cause steric hindrance? So then it would be better to like bind it onto the main group?
Well, this molecule, if I had to guess the shape of this molecule, it's probably pretty planar. So it probably sort of sits like this, and that amino tail probably comes up a little bit. So I don't think you've got it really obstructed either way, because the carbonyl oxygen could probably present itself to the OH, or it could rotate slightly and just go to that amine. So, and then again, these things are so, carboxymethylcellulose, and again is like, could be hundreds of units long. So there is room for possibility, I should say.
Okay.
But I would look more at the most likely or the strongest interaction between the two. The only way to, like I said, to really know is you'd have to get a crystal. You'd have to crystallize these two bound to each other. You know, you do the crystallography, and then you know exactly what the relationship is. But it's not really. It's not a sophisticated, system. So, for example. Usually, like say you got some like a saline solution or just like deionized water, you've got a set amount of your drug in there and it's not soluble, and then you'll take like an array of different size polyethylene glycols or carboxymethylcelluloses, and you'll add it and you just shake and you say, oh, which one goes clear? Right? I mean that's the very first one, and then you start to get the real specific. What is the exact ratio between drug to polymer and so forth? But anyway. Had enough fun?
Yeah.
All right, everybody, I hope you all have a wonderful weekend. Any tests next week?
Yep. Yes.
Oh, Lord. Oh, and then you go on IPPEs, right? Okay, so we're